Hey everyone, you know some liquids, they follow the rules of physics so strangely that they barely seem real. They can climb up walls, thicken when you touch them, flow like metal, or stay liquid far below freezing. For today's video, I'm going to count down 15 of the strangest liquids in the world. Let's start with number 15, ferrofluid. So ferrofluid, it's a liquid that behaves in a way that kinda looks impossible unless you understand the physics behind it. It was invented in the early 1960s by NASA engineer Steve Papel, who needed a liquid rocket fuel that could be controlled magnetically in zero gravity. Now inside the liquid, it consists of extremely small magnetic particles, usually magnetite, suspended in a carrier fluid like oil or water, with a surfactant that's added to prevent the particles from clumping. Each particle is only about 10 nanometers long, and that's small enough to remain in constant motion, which keeps the mixture from settling. On its own, it just looks like an ordinary thick, dark, oily liquid, but once exposed to a magnetic field, it forms these sharp, spiky patterns as the particles align along the magnetic field lines. They form because the magnetic forces try to pull the fluid upward while the surface tension tries to smooth it out, resulting in a balance that creates these cool shapes. Its ability to change shape instantly in response to an external field has made it useful in some practical applications. It's used in loudspeakers to dampen vibrations and carry heat away from voice coils, and it's used in some seals that allow rotating shafts to stay airtight while still being able to spin freely. Although it does kind of look like a solid when it's magnetized, it always is a liquid. The particles inside never permanently lock together, which is why it collapses back into a smooth pool as soon as the magnetic field is stopped. A common misconception, though, is that ferrofluid is safe to touch, but most commercial fluids can stain your skin and surfaces permanently, and they may contain chemicals that irritate your skin. If left near strong magnets for long periods, the surfactant can break down and cause clumping. So the fluid's lifespan definitely depends on storage conditions. That impossible behavior, though, spiky, forming rigid patterns, reacting instantly to invisible forces, has made it a popular subject in demonstrations, art installations, and even scientific displays. This is one of the clearest examples of how a liquid can look like something completely unfamiliar while still operating according to well-understood physical laws. Number 14. Non-Newtonian cornstarch slurry. Alright, that's a mouthful for me to say. It's a simple mixture of cornstarch and water. This exhibits properties that seem to contradict what people expect from a liquid. It's known informally as oobleck. This substance is a shear thickening non-Newtonian fluid. Now, in a typical Newtonian liquid like water, viscosity stays the same no matter how quickly you apply a force. But in a cornstarch slurry, the viscosity increases dramatically when it's subjected to sudden stress. When you move your hand slowly through the mixture, it behaves like a liquid because the water can flow around the suspended starch granules, allowing them to slide past each other. But if you squeeze it or try to move it quickly, the water doesn't have time to refill the gaps in between the particles, and they jam together temporarily, creating a rigid structure that resists force. Once it stops, the structure collapses and the mixture flows again. This phenomenon is called shear thickening, and it's well documented in rheology. That's the study of how materials deform and flow. Now, cornstarch is just the most common household example. The effect becomes more noticeable as the ratio of cornstarch to water increases. At around a 2-to-1 ratio, the shear thickening behavior becomes dramatic enough that people can briefly run across a pool filled with it. And although it's often used as a demonstration or an experiment, the underlying physics is still an active area of research. Some models describe shear thickening in terms of what's known as hydroclustering, where particles form temporary force-bearing structures. Others emphasize the jamming transition, which is similar to what happens in granular materials like sand. Researchers have studied these mixtures using high-speed cameras and stress sensors, and they confirm that solidifying effect is real and not an illusion. There are also some practical considerations. Cornstarch slurry is safe to handle and non-toxic, but it can clog plumbing if it's poured down drains because the particles settle and compact. It also dries into a hard residue that needs to be rehydrated and removed. Its simple ingredients and properties make it one of the most widely known non-Newtonian liquids, and it's a great example of how everyday materials can behave in ways that appear impossible at first glance. Number 13. Liquid gallium. Gallium's a metal, but under normal room temperature it behaves like a liquid with properties that do not resemble what most people expect from a metal. Now, elemental gallium melts at just 29.7 degrees Celsius, that's about 85.5 degrees Fahrenheit, meaning it can melt simply from the warmth of a human hand. This unusually low melting point comes from the structure of solid gallium. In its crystalline state, gallium atoms form pairs. They're held together loosely compared to the metallic bonds found in most metals, and as a result, it takes very little added energy to break them apart and transition the metal into a liquid state. Now, once melted, gallium flows like a thick silvery liquid. Unlike mercury, which remains metallic and shiny across many temperatures, gallium doesn't form a persistent surface oxide layer, so its surface appearance can vary depending on the exposure to the air. It can wet many materials, including glass, much more readily than mercury does. This kind of wetting behavior is one reason gallium can corrode aluminum so quickly. When gallium does come into contact with aluminum, it disrupts the protective oxide layer, allowing the liquid metal to penetrate grain boundaries and break down the metal. This process is well documented, and it's one reason gallium is restricted from being transported on airplanes or through certain facilities where aluminum structural components are used. Gallium-based alloys, which also contain tin and indium like Gallinstan, remain liquid at even lower temperatures and are used in applications where mercury has been phased out due to its toxicity. Gallium is not toxic in small quantities and doesn't release harmful vapors at room temperature, unlike mercury. Another cool property of liquid gallium is that it expands when it solidifies. Many materials contract when they freeze, but gallium is one of the few metals that does the opposite. That expansion can cause containers to rupture if gallium solidifies inside them. And another well-established property is gallium's tendency to supercool. When conditions are controlled and impurities are minimized, gallium can remain liquid below its normal freezing point until it's disturbed. All of its properties have been repeatedly measured and documented, which makes gallium a rare example of a metal that behaves more like a laboratory curiosity, while still being entirely real and scientifically verified. Number 12. The world's slowest liquid, pitch asphalt. Pitch. It's often called asphalt or bitumen. It looks like a solid under normal conditions, but it's scientifically classified as an extremely viscous liquid. Its viscosity is so high that its flow is almost impossible to perceive without any long-term experiments. The most famous demonstration of this is the pitch drop experiment at the University of Queensland in Australia, which began in 1927. A sample of pitch was placed in a sealed glass funnel and allowed to drip freely under gravity, and despite appearing solid, the pitches slowly produced drops at intervals of roughly 8 to 13 years. As of today, 9 drops in total have fallen since the experiment started, and this is one of the longest-running scientific studies in history. At room temperature, it moves so slowly the material feels rigid to the touch. However, when heated even slightly, it becomes noticeably softer, and at high temperatures, it flows readily. Researchers have measured its viscosity to be many billions of times that of water, and independent experiments, including the one started at Trinity College in Dublin, have confirmed the same behavior. In 2013, that researcher in Dublin observed a pitch drop fall in real time for the first documented time in any of the ongoing experiments. Before that, no one had ever directly witnessed a drop separately because the motion is way too slow to detect with the naked eye. So these observations confirmed that pitch maintains fluid properties even when it looks completely solid. The behavior of it is fully understood within classical fluid dynamics. It's not mysterious, but to most people, it appears impossible. These experiments continue to show that even substances that seem completely solid can still be classified scientifically as liquids. Number 11. Supercooled water. So yeah, supercooled water. It's just ordinary liquid water that's been cooled below its normal freezing point without turning to ice. Now, under standard conditions, water freezes at 0 Celsius or 32 Fahrenheit, but if it's extremely pure and kept relatively undisturbed, it can remain liquid at temperatures as low as negative 40 degrees Celsius. This behavior is fully documented in laboratory studies and is explained by how ice naturally forms. For water to freeze, microscopic ice crystals called nucleation sites have to be present. These can be dust particles, imperfections on a container's surface, or even small disturbances like a vibration. When these nucleation sites are absent, the water molecules have no structural starting point for forming an ice lattice, so they remain in a liquid state even when the temperature is well below freezing. The moment a nucleation point does appear, the liquid usually freezes almost instantly, and this sudden transition can be triggered by shaking the container, adding a small piece of ice, or even opening a bottle. These rapid freezing demonstrations have been repeated many times in controlled experiments, and it only works when the water is kept extremely still. Supercooling, though, does occur naturally in the atmosphere, too. High-altitude clouds often contain these supercooled droplets that remain liquid at temperatures far below freezing, and these droplets freeze instantly when they collide with particles, leading to a phenomena like hail formation or even ice accretion on aircraft surfaces. And although supercooled water looks like it sort of breaks the rules of phase changes, it is fully consistent with the known physical principles. The liquid state persists simply because the molecular arrangement required for freezing has no starting point. Every documented instance of supercooled water behaves as exactly expected within established physics, making it an impossible liquid only in appearance, not in reality. Number 10. The liquid that behaves like a solid. Liquid crystal displays. Liquid crystals, they're substances that flow like a liquid but have molecules that can align in an ordered way like a solid. This unusual intermediate state of matter is called the liquid crystalline phase. The most common exposure people have to liquid crystals is in LCD screens, liquid crystal displays, where this phase is exploited to control light precisely at the pixel level. The molecules in these materials are typically organic compounds like biphenyl derivatives. They're elongated, which makes them prone to aligning parallel to one another under certain conditions. Now, in a typical LCD panel, each pixel contains a thin layer of liquid crystal sandwiched between two pieces of glass with transparent electrodes. The molecules in that layer are aligned in a particular direction by microscopic grooves on the glass surface. When an electric field is applied, the molecules rotate and change how they interact with passing light. This allows the pixel to switch between transparent and opaque states when paired with polarizing filters. The switching is incredibly precise, it's reliable and repeatable, which is why the technology has remained widely used. Now, they're unusual because they're neither fully liquid nor fully solid. They can flow when pushed, but their molecular order gives them optical properties that depend on orientation. These optical effects, known as birefringence, allows them to twist or control light in ways ordinary liquids can't. The phase transitions between solid, liquid crystal, and fully liquid states have been measured extensively, and they're well documented. And outside of screens, they appear in temperature-sensitive strips, some biological membranes, and certain detergents. The color seen in mood rings and some thermometers do come from the way liquid crystals reflect with different wavelengths, depending on molecular alignment, which changes with temperature. These LCDs are an example of a strange liquid, not because the technology is unusual, but because the underlying material is a genuine liquid that performs a task often associated with solids. Yet every part of their behavior is supported by decades of experimental physics and material sciences. Number 9. Ionic liquids. Now, ionic liquids are salts that remain liquid at unusually low temperatures, often even at room temperature. Traditional salts like table salt melt at extremely high temperatures because their positively and negatively charged ions are packed tightly into a rigid crystal lattice. Ionic liquids, though, use much larger and more asymmetrical ions, usually made from bulky organic molecules. These irregular shapes prevent the ions from aligning neatly, which weakens the crystal lattice so much so that the salt becomes liquid at temperatures below 100 Celsius, and in many cases below 25 degrees Celsius. This unusual behavior has been confirmed across thousands of synthesized ionic liquids since the late 20th century. This makes them a valuable thing for the process where solvent loss or harmful fumes has to be avoided. Because they don't evaporate, they're used in applications like biomass processing, electrochemistry, catalysis, and green chemistry research. These ionic liquids can dissolve in an unusually wide range of substances like metals, polymers, organic compounds, and even some gases, depending on their specific combinations. Researchers can sort of tune their properties by choosing different ions, and certain ionic liquids are excellent conductors of electricity, while others are used to stabilize reactive compounds that degrade. One of the most frequently cited unusual behaviors is their ability to form structured layers at surfaces. When confined between two charged plates, ionic liquids can form stratified arrangements that behave somewhat like solids, even though the bulk material remains liquid. And although these ionic liquids may sound exotic, there's nothing speculative about them. They represent a class of liquids that challenges common intuition, salts that behave like stable, non-evaporating, electrically active fluids, but every aspect of their behavior is consistent with known chemistry. Number 8. Liquid helium. Now, liquid helium exhibits properties that, to most people, seem physically impossible, yet they're among the most thoroughly documented behaviors in low-temperature physics. When helium-4 is cooled below 2.17 Kelvin, that's about negative 271 degrees Celsius, it transitions into a phase known as helium-2, a superfluid. In this state, it flows with, effectively, zero viscosity, meaning it can move without measurable resistance. This has been confirmed in numerous experiments since the phenomenon was discovered in 1937. One of the weird verified behaviors is what's known as film creep. Helium-2 forms an extremely thin film that climbs container walls and drips over the edge, regardless of gravity. It does this because the liquid spreads to minimize any surface energy, and with no viscosity to resist motion, it continues flowing until the liquid levels equalize. The effect has been reproduced in laboratories worldwide and remains one of the defining demonstrations of this superfluidity. Another verified effect is extraordinarily high thermal conductivity. Helium-2 conducts heat more efficiently than any other known substance. It's often described as more than 1,000 times that of copper. This is not an exaggeration, but a measured fact. Instead of heat being carried by random molecular motion, it's transported through coordinated wave-like excitations. Now, despite the impossible nature of these behaviors, helium-2 is fully consistent with quantum mechanics. It doesn't solidify at atmospheric pressure, even near absolute zero, and because it's zero-point energy that remains even above zero temperature, it's high enough to prevent the atoms from locking into a crystal structure. So, liquid helium is used in applications like cooling, superconducting magnets, and MRI machines and particle accelerators. Every surprising behavior it exhibits has been reproduced and documented. The properties are extraordinary, but not mysterious, making helium-2 one of the most famous examples of a real liquid with seemingly impossible behaviors. Moving on to number 7, the silly putty silicone polymer. So silly putty is widely known as a toy, but the underlying material, a viscoelastic silicone polymer, behaves in ways that don't resemble ordinary liquids or solids. The base ingredient is what's known as polydimethylsiloxane, or PDMS, a silicone polymer with a long, flexible chain. When PDMS is cross-linked with boric acid or borate ions, it forms a substance that flows like a thick liquid, but it snaps or bounces like an elastic solid when struck quickly. Under low stress, silly putty will deform and flow. If you place it on a flat surface, it will gradually spread out over hours due to gravity, and in this sense it behaves like a viscous liquid, but if pulled abruptly, it breaks instead of stretching continuously. When compressed and released rapidly, the material can bounce like a rubber ball because the temporary crosslinks between polymer chains store and release the elastic energy. This unusual behavior was discovered during World War II when researchers were attempting to create synthetic rubber. Instead, they produced this strange material with inconsistent properties. It was eventually commercialized as a toy in 1950, but scientists have since used it as a model system for studying material deformation. This putty exhibits what's known as strain rate dependence. Now, this means that the response of the material depends not just on the amount of force that was applied, but on how quickly that force is applied. This behavior is well documented in materials like asphalt, biological tissues, and certain industrial rubbers. But the combination of long polymer chains, the temporary cross-linking, and high molecular mobility gives it that impossible behavior. It is a rare case where a liquid-like material also behaves like a solid, depending on the timing. But every aspect of its behavior is grounded in experimentally verified physical principles. Number 6. Sodium-potassium alloy. NaK. It's a liquid alloy composed of sodium and potassium metals, and depending on the exact ratio of the two, the alloy can remain liquid at temperatures as low as -12 degrees Celsius, that's about 9.3 Fahrenheit. When mixed, their atomic structures interfere with each other's ability to organize into stable crystals, lowering the melting point dramatically. Now, these alloys are metallic liquids, meaning they do conduct electricity like a metal, but they flow like a liquid. The alloy is highly reactive with water and oxygen. When exposed to moisture, it reacts violently, producing heat, hydrogen gas, and caustic compounds. Because of this, sodium-potassium alloys have to be stored in an inert gas like argon or in a hydrocarbon liquid that don't react with it. Now, it's historically been used as a coolant in industrial systems because of its thermal conductivity. One notable use was in a SNAP-10A nuclear reactor, which was a U.S. experimental space reactor launched in 1965. It used it as the primary coolant, and some early research suggests reactors and heat transfer experiments may also help test metal compatibility and high-temperature performance. Now, another property of it is the ability to wet metal surfaces, especially iron or steel. This kind of wetting behavior increases the heat transfer, but means NAK can creep into tiny cracks or imperfections, which engineers have to consider during design. But it is one of the clearest examples of a liquid that behaves impossibly, a metal that pours like water and ignites violently, yet every property is grounded in research and industrial experience. Number 5. Perfluorocarbons. Perfluorocarbons are liquids made entirely of carbon and fluorine atoms, and they have physical properties that seem kind of contradictory. They are chemically inert, non-flammable, and extremely stable, yet they can dissolve large amounts of gases, especially oxygen and carbon dioxide, far more than water can. This gas-carrying ability has been repeatedly measured in lab studies and is the reason PFCs have been researched for use in medical oxygen carriers, liquid ventilation experiments, and specialized industrial applications. The molecules in PFCs are tightly bound because carbon-fluorine bonds are among the strongest known in organic chemistry. This gives the liquid exceptional stability and near-zero chemical reactivity. They don't mix with water, they don't burn, and they don't break down easily under heat. Some PFCs are nearly twice as dense as water, which allows objects, including small animals, in carefully controlled demonstrations to appear as if they're floating in reverse, with air bubbles sinking instead of rising. This reversed buoyancy effect isn't an illusion. It's simply a result of the liquid's density compared to the density of air. But perhaps the most unusual property is its gas solubility. PFCs can dissolve so much oxygen that they've been tested as temporary blood substitutes and for specialized breathing research. In the 1990s, experiments demonstrated that animals could inhale perfluorocarbon liquids while still receiving enough oxygen to survive for short periods. These procedures were carefully controlled, but the idea of breathing a liquid came directly from PFC's real measurable properties. And they've got exceptionally low surface tension and low refractive index. They spread easily on surfaces and appear almost invisible when objects are submerged in them. Their lack of evaporation under normal temperatures due to extremely low vapor pressure also makes them useful in electronics cooling, aerospace applications, and precision cleaning. Perfluorocarbons are a rare category of liquids that seem impossible. Because of its high density, its extreme stability, and gas carrying capacity, these are all traits that rarely coexist in the same substance. Number 4. Shear thinning fluids. Ketchup. It's one of the simplest real-world examples of a shear thinning liquid, meaning its viscosity decreases when force is applied. This behavior is fully documented in rheology studies and is entirely real, despite seeming to contradict what people expect from a sauce. At rest, ketchup appears thick and almost solid-like. When shaken or squeezed, though, it suddenly becomes runny. This dramatic change in viscosity is an established property of many suspensions and polymer-based fluids. Now, the reason ketchup behaves this way comes from how the particles interact. Ketchup contains finely ground tomato fibers, pectin, vinegar, sugars, and spices. When the bottle sits still, the suspended particles settle into a loose network that resists flowing. This creates high viscosity, but when shear force is applied, like shaking or squeezing or stirring, the network collapses. The particles align and slide past each other more easily. Now, these shear thinning liquids aren't limited to food. Paints, whipped creams, blood, ink, and some polymer melt, and many industrial slurries show the same behavior. This is why paint doesn't drip off a brush when held still, but spreads smoothly when brushed across the surface. One common misconception, though, is that shaking a ketchup bottle loosens the sauce chemically. In reality, it just applies shear stress that breaks the particle network temporarily. As soon as the force stops, the network begins to reform. Researchers have measured these relaxation times perfectly, finding that fluid gradually returns to a thicker state once left undisturbed. Every part of ketchup's impossible behavior, the thick one moment, runny the next, is completely explained by non-Newtonian fluid dynamics. Ketchup may seem ordinary, but scientifically, it shows how liquids can defy everyday expectations while still operating fully within our known physics. Number 3. Liquid nitrogen. Liquid nitrogen is one of the most widely used cryogenic substances in science and industry, and its behavior often looks impossible to anyone unfamiliar with extreme temperature physics. Nitrogen makes up about 78% of Earth's atmosphere, but in its gaseous form it's invisible, odorless, and unremarkable. What changes everything is the temperature. At atmospheric pressure, nitrogen condenses into a liquid at -196 Celsius, that's -321 Fahrenheit. This extraordinarily low boiling point places it in a category where material properties shift sharply. One of the first things you notice when liquid nitrogen is exposed to room temperature air is its violent boiling. This is not because the nitrogen is reacting with air, it's simply absorbing heat. Air at 20 degrees Celsius is more than 200 degrees Celsius warmer than the liquid, so heat flows into the nitrogen immediately and continuously. The heat transfer causes instant evaporation, producing a white fog around the liquid. That fog is mostly condensed water vapor from the air, and it's completely predictable and consistent. A well-studied and dramatic effect associated with liquid nitrogen is the Leidenfrost effect. When a warmer object, such as a metal washer, a rubber ball, or even a gloved hand move briefly above the surface, is brought near the liquid, a thin layer of nitrogen gas forms between the liquid and the object. Now, this vapor acts as an insulation, preventing direct contact and drastically slowing heat transfer. This is why droplets skitter around a table surface instead of pooling up. They ride on their own vapor cushion. Another crucial property is its expansion ratio. 1 liter of liquid nitrogen becomes about 694 liters of nitrogen gas when it warms to room temperature. This expansion is purely physical and has been measured countless times. If sealed inside a rigid vessel, the gas expansion can generate extremely high pressures, which is why cryogenic storage equipment includes pressure relief valves and venting systems. Liquid nitrogen also shows material embrittlement effect. Many materials contract significantly at that temperature. For some polymers and rubbers, the contraction is uneven or too rapid, and it causes them to shatter or crack when stressed. Also, liquid nitrogen is inert. It doesn't support combustion, and this remains true whether it warms from the liquid state or not. And this has led to documented industrial accidents when nitrogen displaces oxygen in enclosed spaces. Workers entering poorly ventilated areas have collapsed due to oxygen deficiencies. And although many people associate liquid nitrogen with dramatic visual demonstrations, the flowers shattering, rubber balls bouncing oddly, or fog rolling across the tables, none of those effects are mysterious. Nothing about liquid nitrogen violates physical law. The impossibleness comes from entirely its temperature range, which is far outside everyday experience, but completely understood by cryogenic science. Number 2. Liquid mercury. Now, mercury is one of the most interesting elements because it violates the most intuitive quality of metals. It's liquid at room temperature. Its melting point is -38 degrees Celsius or -37 degrees Fahrenheit. It's much lower than that of nearly any other metal. Mercury's liquid state is fully explained by its atomic structure, and it's been studied extensively. Now, the reason mercury behaves like this is its electron configuration. Mercury has 80 protons, creating a strong positive charge in its nucleus. This attracts the inner electrons very strongly and causes them to move at speeds where relativistic effects, predicted by Einstein's equations, become significant. One of Mercury's most distinctive properties, though, is the extremely high surface tension, which causes droplets to bead up into near-perfect spheres. Surface tension measurements show how value is far higher than common liquids even compared to water. This high tension also made mercury historically useful in scientific instruments like thermometers and barometers, where a well-defined meniscus is essential for accuracy. Another cool property is its density. At 13.5 grams per cubic centimeter, it's more than 13 times denser than water and denser than many common metals in their solid form. This density enables unusual demonstrations. Solid lead, iron, and even gold can float on Mercury if it's shaped appropriately. A less visible but scientifically important property of Mercury is its ability to form amalgams, which are alloys with other metals. Mercury readily amalgamates with gold, silver, tin, and several others, and this behavior was exploited in a historical gold mining process, where mercury bonded with gold particles to extract them from the ore. However, mercury does not amalgamate with iron, which is why iron flasks were traditionally used to store it. Mercury also has a measurable vapor pressure, even at room temperature, meaning it can slowly evaporate. Mercury vapor, though, is toxic, and its health risks are supported by extensive medical literature. Another cool property is its electrical conductivity, and while mercury does conduct electricity, its conductivity is lower than that of solid metals like copper or silver. This behavior is consistent with the fact that its atomic spacing and electron mobility differ from those of solid crystalline metals. Every property of liquid mercury, the density, the reflectivity, the bonding behavior, the conductivity, the vapor pressure, and its ability to form amalgams, have been thoroughly measured and explained. The only strange thing about mercury is how different it is from everyday experience, not from scientific expectations. Number 1. Liquid sulfur. Liquid sulfur is hands down one of the strangest liquids known to science, because it does something that no other common substance does. As you heat it, its viscosity first drops, then skyrockets by several orders of magnitude, and then drops again. In other words, it becomes runny, then turns into a thick rubber-like liquid, and then becomes runny again, all without ever cooling down or solidifying. These transformations aren't hypothetical, they've been repeated in measured laboratories for more than a century. Now, sulfur is mostly composed of S8 rings, 8 sulfur atoms arranged in a close loop. At room temperature, sulfur exists as a yellow brittle solid, and when heated to about 115 degrees Celsius, it melts into a clear, bright yellow liquid with low viscosity. If the story ended there, sulfur would just be another ordinary molten solid. But instead, sulfur undergoes one of the most dramatic liquid phase transformations known in chemistry. Once molten sulfur warms beyond roughly 160 Celsius, something unusual happens. The S8 rings begin to break open. The atoms don't remain in isolated rings, instead they link together to form long chains. This process is the well-known documented lambda transition. It's also called the liquid-liquid transition, and it's recorded in standard physical chemistry references and phase diagrams. Measurements show how viscosity rising by several orders of magnitude convert the once thin liquid into a dark red, almost rubbery substance. This transformation is real and it's reproducible. Chemically, the behavior is understood as polymerization in the liquid state. The process is fully reversible. If the liquid is cooled back down, the chains gradually revert to S8 rings, and the liquid returns to its thin yellow appearance before eventually solidifying again. If it's heated even further, above 300 degrees Celsius, it undergoes yet another change. The long chains begin to break apart again due to thermal stress. As they depolymerize, the viscosity drops back down. Eventually, if you push it above 445 Celsius, sulfur begins to boil. This entire cycle, ring formation, ring opening, chain growth, chain collapse, is one of the clearest examples in chemistry of a liquid changing its internal structure dramatically without changing its phase. Even sulfur's color changes as the transformation happens. Molten sulfur begins as a pale, transparent yellow. As the polymer chains grow, the color deepens into orange and then to a dark reddish brown. And if molten, polymer-rich form is cooled rapidly, it doesn't immediately crystallize. Instead, it can form a long-lived rubbery solid known as plastic sulfur. Plastic sulfur was first documented in the 19th century, and its behavior has been studied with modern analytical tools. But most liquids behave predictably as they're heated, usually becoming steadily thinner as molecular motion increases. Sulfur is a remarkable exception. It actually becomes thicker, much thicker, before thinning again, all because its molecules are spontaneously reorganizing themselves on the atomic level. Liquid sulfur remains one of the most extraordinary examples of a natural element whose liquid behavior defies our intuition, while remaining entirely consistent with known chemistry.